Okay, everyone, good morning. So today I'm going to assign the first lab project, and we also have our first quiz on Blackboard. So you have till Friday to take that. Just log in, there's only 7 questions. If you have any problems, let me know. It's the first time I've done quizzes in Blackboard. I had to write a script to convert my Moodle questions over to Blackboard. So if you see anything odd, let me know. Okay, so last time we talked about pulse width modulation, and I said that it's a way to modulate an analog value on a digital pin, and it works by creating a periodic signal according to a fixed frequency or period, right? Period is measured from rising edge to rising edge, so that in PWM that period stays consistent. And then the duty cycle can be varied. And so the duty cycle is the percentage of time that the signal is high versus low. And that's used to encode an analog or continuous value. This example shows DC values. So this would be like a 10%, 50%, 10, 25, 50% duty cycle. You can also modulate a AC signal on there as well. So I showed an example of that. And then I had a question about that. And then interrupts. Talked about interrupts. Interrupts are a way for a peripheral to interrupt the CPU. You may be looking at the ESP32 and wondering where the interrupt pin is on there. There's no interrupt pin. There's 48 pins on there. None of them are labeled interrupt. I don't think so. Maybe you can configure one as an interrupt. But when oh, okay. So, but when what I'm talking about here though is on chip. So the idea is that we've got this internal interrupt mechanism going between the on-chip peripherals and the CPU. And the interrupts are basically just a wire that's sent back from the peripheral to the CPU. And they're meant to cause the CPU to execute an interrupt service routine that could either be in the operating system or something that you write if you're doing bare metal coding. And then there's different protocols for interrupts. So this is a level triggered interrupt where when the interrupt is high, it causes the CPU to see the level high, goes into the interrupt service routine. There's also edge triggered interrupts. On the Atmel chip, you could actually configure which one you wanted. You could make the interrupt hardware was programmable. But what it didn't have on there, what the Atmel chip didn't have was an acknowledgement mechanism for interrupts. So the problem here is that if you hold the interrupt high too long, you may inadvertently trigger 2 interrupt service routines, or you may try to issue multiple interrupts within the time it takes to run 1 interrupt service routine on the CPU. So to avoid these kind of problems, you could come up with an acknowledgement mechanism for interrupts. This is the way that higher end CPUs do it, where the peripheral issues an interrupt request. The CPU acknowledges it, at which point the peripheral would then drop its interrupt request, and then the peripheral would know when the interrupt has been serviced by when the acknowledgement goes low. So it's like basically a 3-way handshake. And then we switched topics again and started talking about chip-to-chip protocols, chip-to-chip communication. So now we're moving off-chip. Right, so when I was talking about the interrupts, that was kind of an on-chip thing that was going on in there. Programmed I/O was also an on-chip thing where you had the CPU talking to the peripherals through load and store instructions. That was being done through the on-chip interconnect. Now we're talking about channels that go off-chip onto the circuit board or onto a cable, right? And so we talked about different trade-offs there. Just like with anything else, you can have high-performance protocols and low-performance protocols. We're going to deal with mostly low-performance protocols. Of those, you've got asynchronous and synchronous types. Asynchronous is when there's no clock as part of the channel, whereas synchronous is where you have a clock. And the first one we talked about was SPI, which is synchronous. It stands for Serial Peripheral Interface. And this is not only is it synchronous, it's also a master-slave type interface where the master initiates the transactions on the bus. and the slaves are on there and they respond. The idea is that the master is usually a CPU and the slaves are I/O devices, sensors, actuators, that kind of stuff, peripherals. We got into some detail here. There's 4 signals, clock or S clock. I don't know why it has to be S clock. Clock is good enough, in my opinion, but we call it S clock for serial clock. Then there's MOSI and MISO. MOSI is output, MISO is input, and SS is slave select. SS is active low, meaning when that's low, you're using the channel, essentially. The clock is only clocking when the channel is active. So the SPI is built around this concept of an exchange where you've got a value, a byte on the master side and on the slave side, and they're swapping. They're atomically swapping. But I mentioned that in practice, I've never seen a case where this exchange functionality is actually used. This bidirectionality is used. But that's how SPI is designed. It's designed as like a shift register almost, where you're shifting bits out while you're simultaneously shifting bits in, right? And so you could think of the shift register as having the MOSI is between the bits shifted out of the master into the slave, and then MISO is slave coming back in the master. So there's SPI has, unfortunately, SPI, I don't know what the history of this is, but SPI seems to me like it's kind of loosely defined. I don't think it's governed by an organization that enforces the adherence to the protocol. It's kind of an informal protocol in that sense. And I think that's the reason why there's these different timing modes, right? There's different ways to interpret. There's different subtle ways, very subtle ways to interpret these signals. And those subtleties are exposed through this CFA and CPOL. CPOL is where the clock is at when the channel's not active, which can be high or low. And CFA is really just defining when the data changes relative to the clock. So when CFA is 1, when CFA is 0, the clock gets a half a cycle head start on the data. Right? So I showed these 4 timing diagrams. By the way, is everyone comfortable reading timing diagrams? You've seen these before? Oh, you've seen these in 611, right? That's why, forgot. That's why we have 611 as a prerequisite now. So you should be comfortable with reading these. So you could think of these things as they look kind of like model sim, right? Or Quest to Sim in 611. So when CFA is 0, I'm sorry, I said that backwards before. Sorry, when CFA is 0, the data has a head start on the clock. Sorry, I had that reversed a few seconds ago, right? So the data is changing. Maybe changing is the wrong word. The data is going into its kind of stabilized form, right? A half a cycle before the first clock edge of the exchange, right? So you see that there's a half a cycle here between where the data changes the first time and the clock changes, right? Whereas if CFA is 1, everything happens at the same time, right? The data and the clock all change at the same time. So what that means is that if CFA is 0, the data is sampled on the first edge of the clock. And if CFA is 1, the data is sampled on the second edge of the clock, right? Now you might hear that and say, oh, well then I guess that means there's 1 extra clock cycle if CFA is 1. No. Same number of clock cycles. If you count the number of edges, in both cases, it's actually 8. Falling, like if I go from rising edge, 1, 2, 3, 4, 5, 6, 7, 8. 8 rising edges, 8 falling edges when CFA is 1. There's also 8 rising edges and 8 falling edges when CFA is 0. So it doesn't change the number of clock ticks or the clock pulses or the number of edges. They all stay the same. And the reason is because the difference it makes is a half a clock cycle, right? So the CFA makes a 1/2 clock cycle timing difference. But it's very important, it's an important distinction, because if you don't have that half clock cycle, you end up trying to sample at the same time that the data is changing, and that's going to lead to errors, synchronization errors. You won't be able to read data in that condition, right? So it's it's subtle but important distinction. And then what about C-pole? Why is that important? C-pole is going to determine what edge of the clock you're reading data on, right? Given a value of CFA. So if you know what CFA is, you then have to know what C-pole is to know what edge your flip-flops are active on the receiving side. Make sense? And remember, there's two receiving sides. Both the master and the slave both receive because it's a bidirectional channel, even though no one, in my experience, uses it as such. Okay? Everyone, any questions about that? Okay, so whenever this slave select is down and the channel is active, all of the number of clock cycles will be a multiple of 8, right? So at minimum, I'm showing 8 cycles here, but you could keep the channel active after these 8 bits are exchanged to transfer additional groups of 8 bits. But the number of cycles has to be divisible by 8, multiple of 8. Okay, so I think I did this question last time. Okay, so then I mentioned there's the terminology is a little funky here because there's an exchange, and then you can build transactions on top of exchanges. The intent of a transaction is to create a programmed I/O style interface where I can read from an address or write to an address on the other side. So that's the purpose of a transaction. Transaction is an abstraction that sits on top of an exchange. The problem is that the transaction protocol is fairly consistent in the sense that the first exchange is like a header, right? And then the following exchanges are payload data, right? But the format of that header and the way the header is interpreted is completely up to the vendor, of the peripheral you're talking to. It's not standardized. It's not enforced. Because again, SPI is it's a very informal protocol. So in order to use SPI, you have to look up the data sheet of the peripheral that you want to communicate with and use whatever protocol it describes in there. So so as I mentioned, if you do a read operation, the first byte, and maybe the second byte too, but the first byte or two is going to be some header, some preamble, and then you expect the payload bytes to come back to the master through MISO, right? On the other hand, if you're writing, you have the preamble stuff comes out of MOSI, and then when you write, you send the data that you're writing through MOSI as well. Make sense? So the point is that there's no bidirectionality here. Throughout the transaction, you're only using MOSI or MISO. They're mutually exclusive, and the other one's dead, right? So you see something like this where here's a read operation. So there are 16 clock cycles. The first 8 clock cycles are sending out some bit that says whether I want to read or write, whether I'm doing a single or a multiple read or write, then the address bits. And then in the second 8 cycles, we just have data coming back and nothing going out anymore, right? So that's why we have flat line here and a flat line here, right? Flat line here because I don't need to do anything. I don't need to send any data after I send out the kind of the header byte. And there's a flat line here because I have to get the header byte to the peripheral before the peripheral knows how to respond. So there can't be any simultaneous transferring here. So here's a write transaction. In this case, I didn't even show the MISO. This is only the MOSI. Notice that the names are a little different though. Even the names aren't standardized in SPI. So now we have chip select and SPC, serial peripheral clock, I guess that probably stands for, and serial data in. So be aware that names sometimes are also different. Okay, so here's another example. So just looking at this, I could tell that it's probably a right because meso is flatlined. I can also tell that CFA is going to be 1. Even without looking at this, I know CFA is 1 because clock and data change at the same time. All right, so I'm going to go to the second edge, and I can tell just from looking that the edges I'm reading on are rising because the rising edge is the second edge. So you don't really have to look at these guys if you have the timing diagram, right? If you have the benefit of seeing the timing. And then so how you read this is kind of obnoxious, but you have to just decide where you want to look at MOSI and MESO. You should use vertical lines kind of to help you. So in this case, I drew vertical lines because the other way to do it is to just look at where, the dotted lines are intersecting the sampling edges in this case, right? So I could just look at the dotted lines, dotted line, wherever the dotted line intersects the data line is where you're going to read, right? But I drew these other lines in here straddling the dotted lines to show, the transition points, which is probably overkill, right? Makes sense. Now in this case, I'm sending these bits most significant bit first. These could also be reversed. I think SPI is typically MSB first. I think. I'm not sure about that because again, it's a loosely defined protocol. It could be either way. But make sure that that was something that the peripheral documentation would tell you. I think on the Arduino, on the AT Mega chip, this was a setting. You would just tell the hardware CPOL, CFA, and then MSB or LSB first, and then the hardware would work that out for you. But you'd have to tell the hardware that before you start communicating with the peripheral. Okay, so then, so in this case, what are we doing here? The least significant 5 bits of the header is the address. Read-write flag is the most significant bit. And read is 0, write is 1. So I could tell that the read-write bit is 1, so that's a write. But I didn't even need to know that, like I said, because MESO is flatlined. I could tell it's going to be a write. Okay. I mentioned that because MESO is not active during the first exchange, I'm saying that these are don't care bits. Meaning that the slave is going to ignore those bits. So even if the master were sending data, or if the slave were sending data during the first exchange, the master would ignore it. Likewise, it would do so during the second exchange as well. Okay, and then here's an example of a read. Everyone feel fairly comfortable with that? Reading those things? Okay, so the problem there is that I only showed one read or one write. If you're reading a sensor that maybe has 32-bit registers in it, you can't read a whole 32-bit register with one of those types of transactions because there's only 8 bits conveyed. Generally, you also see the capability for multiple read, multiple writes, where the header will have a bit in it to signify whether you're doing a kind of a streaming operation, multiple bit, multiple byte read or write. Now, the way that you implement that, though, can depend on the protocol. So in some cases, if you do a multiple read, multiple write, the second byte sent by the master will be the length of the transaction. But in other cases, you don't have the length. You control the length just through the slave select. So if you set up a streaming read or write, the slave is expected to participate for as long as the slave select is low. It just depends on the protocol. So in this case, this one is just saying there's a bit in bit 6 of the header byte called multiple or single. Single is a 0, multiple is a 1. And if that bit is 1, then it's assumed that you're just going to start at whatever address. You start the read or write at whatever address is specified in the header, and then it just continues indefinitely for as long as the CS is low, or chip select, slave select. And then it's implied, of course, that the address is ticking up, right? So you're providing a starting address in that header field. So in this case, we have 1 transaction and 3 exchanges. Okay, so here's a multiple read using the same protocol. And by the way, just to clarify this, sorry, not that one. This timing diagram looks different because I actually took this from the data sheet of an accelerometer that we used to use in the class. This other timing diagram, I wrote a script that generates LaTeX code with the TEEX library to generate these. So these ones are custom. That's why I have a mixture of different looking timing diagrams. This one is a multiple read, and you can tell you can just tell from looking at it, that MISO is flatlined in the first transaction, and then you've got the first exchange. I still screw that terminology up. The first exchange, which is the first 8 bits of the transaction, MISO is dead. And then, there's two exchanges after that where you've got activity on MISO. So I'm reading 2 bytes from the slave in this case. If you decode it by figuring out where all the bits are in here, you can see that the first bit is 0, which indicates a read. Second bit is 1, which indicates a multiple read. And then the address would be 1110, which is 14. And so I'm saying start at 14, and then I'm getting address 14 and 15, right, with this, right? 15 because, the second exchange would increment that address, right, implicitly. Okay? So here's a multiple write. Here's another multiple write. In this case, I've got... you can tell it's writing because MISO is flat. And so if you decode this, you have to just figure out what the bits are. And this one is CFA 1. And so I'm going to look at the second edge, and I'm going to sample on the second edge. So, 1 1 1 1 0 0 0 0 1 0 0 0 1 1 1 0 0 1 1 1 0 0 0 1. Okay. Okay. All right, so this leads us to lab 1. So, I have some, not in the first quiz, but the second quiz, I'll have some timing diagrams I'll have you interpret. But for lab 1, we want to write a program to decode these things, decode these transactions. So the idea is to read a trace file, which is a text file that contains essentially what you see in the timing diagram. It's just a text file with lines, with rows, and each line is a time, has a timestamp, and then the columns are the values that were sampled at that time. Make sense? So it's like reading an oscilloscope or a logic analyzer and just saving the data as a file, right? And then we're going to read that and then decode what's going on in there as a English interpretation of what the transaction is doing. So read or write, followed by the address, followed by whether it's single or multiple, followed by the data, right? So there are tools that do this, which inspired us when we designed this lab. There's a tool called SIGROC, open source tool that is designed to do exactly this. And these oscilloscopes do it too. Of course, we had to pay like $1,000 per scope to get that capability. Despite it being fairly simple, something that we can do in this lab. But yeah, so that's basically the idea, is that we want to convert these things to transactions. So this lab has hundreds of test cases in it. And there's a grading script that automatically grades. So we have test cases. you just run the grading script with your code, and it runs a diff, the Linux diff command, to check the differences between what we expect the answer to be and what your actual answer is, right? So when you write this code, you have to make sure that that whatever you're printing to the console, at least on standard out, matches exactly what we tell you to print, because we're going to be doing like it's automatic grading script. Now you can, if you like to debug with print debugging, you can still do that through standard error. You can print standard error, but don't print the standard out if you're printing debug messages. Of course, you can also use the debugger, right? You have the option to write this lab in C or in Python, whatever you're more comfortable with. Although, surprisingly, in the last, actually ever since we came up with this lab, almost no one writes it in Python, which surprises me. I thought everyone's doing Python these days, but yeah. I mean, we opened up this choice because we expected that to be what everyone's doing, but anyway, okay. So here's an example trace. Now, originally we had an intro lab to this where we just had you reading parallel data, but we skipped that one now. We go straight to the second lab, which is actually interpreting this as SPI. So you'll notice that in this case there's 8 signals, which doesn't make sense because SPI is only 4 signals. But this was because, like I said, we did originally have this version where we had 8 bits in there. So the problem is that the signal trace file does not have a consistent sample rate. Because if it did, it would be very wasteful, because if the signals aren't changing state, there's no point in measuring at fixed intervals if nothing's going on, right? So what we have in here is a case where the samples are only recorded in the file whenever something changes, which means if you look at the time axis in the file, the first column, which is the times, they're not at a regular, it's not like pulse width modulation that's always according to a fixed period. It looks kind of strange because you've got time jumps in there, all right? But that's because you have to assume that if there's nothing listed, there's no timestamp then the signals are just not changing, right? They're just maintaining their state. So in this case, I'm showing this might be, maybe this is too much detail, but basically I'm showing a 1 millisecond fixed interval down here on the horizontal axis, but the ones that are in red are the ones that are actually listed in the file, because the red lines are indicating whenever something changes. In some cases, 2 signals change. Like in this case, S0 and S1 both change, and then I log that time at 3 milliseconds, but nothing changed at 2 milliseconds, so there's no 2 millisecond in the file, okay? All right, so this is what the textual form of it looks like. So this is a bit confusing because we use a tab-separated format. So the first line is the number of samples, the number of rows, the number of lines, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, start here. 1, 2, 4, 6, 8, 10, 12. Yeah. So there's 12 lines after starting on the 4th line, right? There's 12 lines starting on the 4th line. Why starting on the 4th line? Because the first line is the number of samples. The second line are the names of the signals, the names of the columns. And then the third line is the bit width, which is a little redundant because in SPI, all the signals have 1 bit, But again, I think at one point we were imagining that we're going to do more with this. We'd have some parallel signals in there. But these are all, so you're just going to see all 1s in that 3rd row. And then you've got time, and then the corresponding values of each of those. The thing that makes this confusing is that for whatever reason, we don't have a column header for time. Okay, so what you see is that it looks like the last column has no header, but that's because we actually don't have a column header for the time column, right? So just be aware of that. Right. Okay, so then we also provide an API for you to use. You don't have to use it. But we have a C and a Python API. So if you're writing in C, we have a type called waves that is meant to be the handle to the waves, right? So you declare a wave pointer, which I called myWaves. In Python, you do the same thing, except you use the Pythonic way of doing it, which is say myWaves equals waves, like you're calling the constructor for it. I don't like that syntax, but that's how Python does it. And then you're going to assign that pointer in C by calling parse file. And the file you're going to parse is standard in, because the grading script pipes the trace file directly. It shoves the trace file down the throat of your program, essentially through standard in. So you're reading just from standard in. In Python, you just say mywaves.load text sys.standardin.read. Okay? Okay, then once you do that, you have basically two functions you use: next edge and read, signal at. Next edge and signal at. So the waves object that you're creating is stateless. It doesn't keep track of where you are, what time you're at. Which, I don't know, maybe we should have had we should have made it stateful. But the way we're doing it is you have to keep track of where you're at in the file. So you need to have a variable called time. So you'll start time at 0. And then when you march through the file, all you have to do is say next edge. And then you say after, you assign after, right? So this after input is where you're currently at, and you want to find the next edge after that time, right? And then it returns the edge time, which then you will, of course, assign. I might be giving away too much, but you assign the return value of this to your time variable, right? So you say time 0, find the next edge after 0. This will return, say, 10 milliseconds, at which point you're going to reset your time variable to 10 milliseconds, and then you look for the next edge after 10 milliseconds, right? Make sense? So it works the same way in C and in Python. Very similar. So you look for the next edge using the waves structure, or object, I should say. The signal that you're looking for the edge on, which is clock. The after, which is where you want to start from. And then there's the two flags, positive edge, negative edge. You can have them both true, in which case you're looking for the next edge, whether it's falling or rising, or you can just set one of these to true and the other to false if you're just looking for one edge or the other, right? And then there's another function that's a little simpler. It's just called signal at, where you just give it the waves object, the signal name, and the time. And it'll just read back the time. Make sense? So we're measuring when the signal changes, and you read it at that change. And when you so if a signal changes and you read it at the time that it changes, you're reading the new value of the signal. Just to clarify that, right? So if there's an edge at 10 microseconds, you read it at 10 microseconds, you're reading the updated value of that signal after it had changed, right? Okay? That make sense? So when you have an SPI transaction, obviously it's all based on the edges of the clock, which is where you're supposed to be reading. So you're pretending like you're sampling the signal. And of course, you have to also find where the transactions are. Each one of these trace files has multiple transactions in it. So it's not just one. You have to go through, you have to scan through the whole file. Okay? Okay, and then as I mentioned, you can, we have a function called log, which actually just prints a message on standard error, which you can also just print to standard error yourself. And then in Python, we actually don't have a log function. You just write to standard error. Okay. Okay, so yeah, so there's an example of that. Oh yeah, this is the format we're using. So we're going to switch this up a bit. In this project, the address is the most significant 5 bits. 6 bits. 7902, 6 bits. The first 6 bits, the most significant, the first 6 bits is the address. And then bit 1 is read or write, which is 0 for read, 1 for write. And then bit 0 is single or stream, 0, 1. Right? So, and then if stream happens to be 1, so by the way, if you read this value, this transaction, then your program should print RD space 11 space 1A, meaning that we're reading. The address is 11. Why is it 11? Because remember, it's only 6 bits. So when you convert a binary value to hex, but the binary value does not have a multiple of 4 bits, because remember, hex digit is 4 bits. You have to start from the right and work your way to the left. So 11 means 1 is this hex digit here, 0001. And then the next one, you only have 2 bits left over in the address, which means that the next significant hex digit can only be 0 to 3, right? So the address will range from 00 to 3F, right, is the range of possible addresses with 6 bits. And then the data is 1A. The data is 8 bits, so you can just do 4 bits and 4 bits. So that's 1, and then 1010 is 10, or A in hex, right? So you have to make sure you use that format so we can do the auto grading. Likewise, if it's a write, same thing, except you're gonna print write, WR, right? So this is writing the value of 39 to address 3B. So it's RD or WR, followed by the address, followed by the data, and then the values are in hex. 2 hex digits. Make sure that they're 2 hex digits. So if you have a leading 0, you have to include that. Okay, now for streaming read or write, a streaming read or write would be indicated by the least significant bit of the first exchange. And so if it's 1, this is where we change things up a bit. If it's a streaming read, then we have the master send a second byte to the slave indicating the length of the stream. So in this case, we're doing streaming with two data exchanges, 2 data words. And so you can see the 2 data words here. So we're reading 2 words starting at address 14 in hex, right? So this is 14 in hex. We're reading, it's streaming, and there's 2 bytes. And so that means that after that 16-bit header, there's going to be another 16 bits of data, which is F and, what is that, 8 plus 3, that's B0, right? Yeah, so that one should print read, stream, address 24, data 0F, B0, right? Okay, so this way, you interpret the signals as, like I said, basically almost like an assembly language or an English. Yes?
You know if there's an upper limit on the stream length that you have in there, or is it just a full, whatever you can put with 8 bits?
Yeah, I think it could go up to 255. I don't know if we have any that are 255 length. That's a good question. I never checked that. They were generated randomly, so I'm not sure. Good question, though. I think most of them are fairly short, as I remember. There's a write, so we could do a write. Okay, and then finally, one last detail. So what about CPUL and CFA? Because that's going to affect how you're decoding these. So we're going to provide CPUL and CFA will actually be signals in the trace file that you can read out, but they're DC. They don't change. So you can just read them at time 0. Okay. Now, the lab is going to be split into 3. Hold on, let me bring up the lab sheet here. So I've got the lab sheet posted on Blackboard. Sorry, my memory is shot. Blackboard, yes. It's posted on Blackboard. It's going to be due. We got 2 weeks. Should be enough time. Well, yeah, like 2 weeks starting from today, roughly. Friday, January 31st. We have this split, it's very 11 pages. We went a little overboard with this, but it has all the details in here. And it's pretty much what I explained. The only detail I didn't mention here is that there are 3 parts. The first part is where we limit the transactions to non-streaming, and CPUL and CFA are locked in at 0, 0. Okay? In part 2, we add streaming transactions. And then in part 3, we add the ability to change CPUL and CFA, right, on a trace-by-trace basis, right? So your code will have to, just basically read those, and then the code will have to be slightly different when interpreting the data. Make sense? Okay, so obviously this is just a programming project. This will be the only programming project. After this point, we'll be using hardware. What's that?
I said, woohoo, even more error.
Yeah, you're right. That's true. It's, okay, so there's a lot of documentation about the infrastructure that we give. Okay, so the problem with all this, though, is I've showed you how to interpret these with waveforms, right? But now I'm saying you have to interpret them with either a text file. You can open those text files, which they're huge, or you can write your code and debug your code, and as you debug your code, you're trying to figure out what's in there. That's kind of rotten. We need a way to visualize those traces as graphics, as waveforms, right? And luckily, we do have a way to do that. I think it's helpful for debugging. So you'll download the skeleton. So we have a skeleton on Blackboard. It's called lab_spi.tar.gz. So you just untar that, and then you go in the directory. Can you read that? Is that?
Yeah.
Okay. Okay, so you go in that directory, and there is a code C and a code Python directory. And in there, we've got basically starting points for you, right? Templates, right? You're going to want to choose which one of these you want to use. And once you choose which language you want to use, you want to rename the one that you chose to just code. Okay, so if I want to use C, I would do move code C to code. That's step 1, right? Then the next thing you want to do is put a file in that directory with your username. And if you forget to do this, it'll print an error and tell you to do this. But I'm going to echo my username, and I'm going to put it in code in a file called userid.txt. Okay? Then you basically just run the grading script, grade.sh. Okay, now this is, right. So this will grade. It'll stop grading whenever it encounters an error. So there's hundreds of test cases, but it stopped after the first one. So what it printed was, and this I'm not super thrilled with, but I think it is good to learn how to read these diff files. So what it's printing is a diff file or a patch file, Linux patch file. So what it's saying is that it's on part 1. This is the weight of that part 1, 0.72. And it says your program exited without error, but your output did not match what was expected. And this is the difference between the actual and expected output. So the actual was nothing, because my program didn't print anything, because I didn't add anything there yet, didn't add any print statements. And the expected was shown below. And you can ignore this part of the expected is not actually expected. This is the index within the patch file where these changes occurred, right? So if you ever use diff in Linux, this is I don't even know how to read this. This is some kind of code indicating where the differences start, right? And probably maybe where they end. I don't know if 64 lines, I don't know. I don't know how to read that. I don't know diff. But then down here, we've got plus. Plus means this is stuff that's in one and not in the other, right? So plus, these are all the things that you should have printed, right? So these are all the transactions in that file. And that's just one file. That's just one of the trace files. Each trace file has a bunch of transactions. And so you can see that's essentially the answer that should have been printed. Now, how do we look at the actual waveform? So to do that, there is an option called text to VCD. VCD. VCD stands for value change dump. It's just a text file that's used for, it's basically a text file that's doing the same job as the trace file I just described, except it's a different format, different syntax, right? It's a standard syntax. Ours was, that one I showed you, we invented that one. That's just our proprietary one. So you give it that option, and then you give it the test case. So if you go to test cases, part 1, and then we look at test case part 1, 001, and then inside there, so the test cases have part 1, part 2, part 3, and then in each one there's multiple tests. So in part 1 there's 28 waveforms in part 1, and inside that directory there's an input, an output. Output is what we saw in the diff, what it expects you to print. Weight, which is the grading weight, and category. I forget what's in there. Probably, I don't know. But we want to look at input, right? Input. So you just say convert input.text to value change dump, then you give it a name. Wave. This is all in the README file, by the way, so you don't have to memorize this. So I'm going to call it VCD, wave VCD. And then if we look at wave VCD, it's pretty straightforward file format. It just, whenever there's a change, it indicates which signal changed. What it's showing here is 6 signals. There's clock, ship select, MOSI, MISO, and then there's CPUL and CFA. And each one of those signals is indicated with a symbol. These are the symbols that point, and then the symbols are defined up here, right? And so to read that graphically, use a program called GTK Wave. And you just open it with that. This is an open source waveform viewer. And so you have to drag the signals in you want to look at, or actually right click and insert. Yeah, there you go. And then you just zoom full. And you can see this is a graphical representation. So there was 28 test cases. I forget how many transactions there were. But each transaction is, when slave select is 0, right? So if you look at slave select, you can actually just see whenever that's 0. So every period of time between these little blips in slave select is a transaction. And then MISO and MOSI are the signals. And then the clock is, you can see the clock is only active when slave select is low. And then you can also, zoom in to get a closer look. Look at what's happening there. There you go. So there's a transaction, and every one of these should be exactly 16, because these aren't streaming. So every one of these transactions is exactly 16 cycles. So there's 16 cycles, and then you can see the data. So this is just for debugging. You don't have to use it, but if you don't use it and you have an error in your code, it's kind of hard to figure out what's going on without seeing the actual signals. Any questions? We'll give you all the time that we have allocated for class to work on that. And I'll be here with the TA to answer questions. We're hoping that most of this semester you'll just be working in the lab and I'll be walking around answering questions. Trying to get through this conceptual stuff as fast as I can. Okay, so yeah, that's lab 1. So let's move on now to the second topic, is UART. So this is another protocol. Stands for Universal Asynchronous Receiver Transmitter. It is actually asynchronous. There's no clock in there. I talked about this a bit last time. The way it works is each side of the channel generates its own internal clock, which the frequency of which has been agreed upon. And then you just hope that whatever edge of the clock you sample the data on, you just pray that the other side of the channel isn't changing the signal at that exact time, in which case, if it does, you're likely to get an error, right? But UART has built-in error detection to deal with that. And also, UART is really super, super slow compared to SPI. So SPI is single or double digits megabits per second. This guy is like kilobits, double-digit kilobits. So basically, it's just 1,000 times slower than SPI, 100 to 1,000 times slower. Which means that because of that slowness, it's less likely you're going to try to sample a data during a transition, but it still happens. Okay? The good news, though, is it's really simple. You just have one transmit wire and one receive wire. And then there's a common ground, but that's kind of redundant because we also assumed that SPI had a common ground too, which I just didn't show it in case of SPI, right? So these are not decoupled. These are electrically coupled in the sense that we have a common ground. Okay, so the way UART works is that when the channel is idle, the signal is high. Right? So it's bidirectional, so there's data going in both directions. So you can treat each one of those wires is acting independently. It's not like SPI when you have a transaction, both MOSI and MISO are active at the same time. With UART, they're sort of independent. Transmit and receive are just two independent channels, and whenever they're inactive, they're high. Whenever you want to send something, you have a start bit, which is when you drop the signal to ground for exactly 1 bit time, the period of the clock. And again, the clock has been pre-agreed upon what that speed is, just not the phase, which is the problem. But we know what the frequency of the clock has been pre-agreed on. So you drop that for 1 bit time, whatever the bit time is. It's the reciprocal of the clock rate. Okay. Then the next 8 bit times, you just have 1 or 0. And then you have a stop bit at the end, which is where the bit has the value has to be high for at least 1 bit time at the end. All right? You might say, well, that's kind of, wait a minute, it's normally high, right? The signal's normally high. So what does it mean to have a stop bit high? Stop bit high just means the channel's idle, right? Well, not exactly. The stop bit means that you have to keep it high. In other words, what the stop bit is doing functionally is it's forcing all the transactions to be separated by at least 1 clock period, right? So that way, if I want to send 2 consecutive values, I can't really make them consecutive in the sense that there's that stop bit that's serving to separate 2 values. Does that make sense? That's all the stop bit does.
Well, what if you want to send 3 high bits at a time? How does it know the difference between that and the stop bit?
Because that's a good question. When a transaction is happening, the number of data bits is also agreed upon, and so it's always 16 or 8. Yeah, right. It's almost always 8 in practice. So in addition to the clock being pre-agreed upon, the number of data bits is also pre-agreed upon. So there's a counter going on. You're keeping track of what bit you're on, right? Okay, so yeah, I already talked about that. Okay, so then there's also some other, there's another feature I mentioned, there's error detection. So if you have error detection turned on, and this is an optional thing, again, has to be a pre-agreed upon, it's called a parity bit. So you have whenever you have parity, which you almost always do have parity, there's the start bit, there's the data bits, then you have a parity bit, and then the stop bit. The parity bit can either be set to even parity or odd parity, which is another thing that has to be pre-agreed upon. However, this is wildly confusing because if you have even parity, you would think that that means that if there's an even number of 1 bits, then the even parity indicator should be 1. That's what that's what I would guess, right? Makes sense. But that's not how it works. It's actually the opposite of that. If you're using even parity and there's an even number of 1 bits in the channel, the parity is 0. So it's kind of active low, right? But the real rationale for that is that what you're supposed to do is count the number of 1 bits in the data section of the packet or the transaction and the parity section. And if it's even parity, then the total number of 1 bits should be even. Meaning that if there was an odd number of bits in the data, you would set the parity to 1 to even it out, right? Basically, right? And if there was already an even number of data bits in the parity, you'd set the parity bit to 0, right? And likewise for odd. So the parity bit is meant to logically be part of the data and force it to have an even number and odd number of 1 bits. Make sense? I was confused. I don't know why they did it that way. And then there's the baud rate, which is the clock frequency of the channel, right? And you might say there's a distinction made between baud rate and like throughput, because the baud rate is how long each slot, how much time is allocated to each slot in the channel. But the data rate is the effective data rate is the baud rate multiplied by how many data bits you have in each transaction. So if there's 8 data bits, but you need to have the start bit and the stop bit and the parity bit, there's 11 total bits, right? So the throughput is going to be the baud rate times 8 over 11, right? Make sense? But the baud is the agreed upon local clock. Okay, so here's an example. And as I mentioned, I wrote a program that generates these waveforms for the lecture slides and for the exams and stuff. However, you can tell by looking at my waveforms here is that this was obviously derived from my SPI code. And as a result, you'll notice that the transmit and the receive are kind of synchronized, almost like we're doing an exchange. But you don't have to necessarily do an exchange on UART, right? You're not necessarily always going to be transmitting and receiving at the same time. So try to ignore that for the time being. So in this case, there's 7 data bits, which is possible but uncommon. 7 data bits, least significant bit first, no parity, and in this case, I'm saying there's 2 stop bits, which is also possible, although uncommon. So 2 stop bits just means separate each transaction with 2 idle times, 2 idle cycles. Notice there's no clock, so when you read this, you just have to look at where the transitions are and just look at between the transitions. Okay, so this is in the transmit side, we have a start bit, which is low. Right? Start bit is low. You just have to remember that. Which makes sense because the channel is normally high. So start low is it's when you're changing, the channel's coming alive because we're changing it out of its idle state. So start bit is a low, and then we have to count 1, 2, 3, 4, 5, 6, 7. So we just count 0, 0, 0, 0, 0, 0, 1. However, we have to reverse it because it's least significant bit first, right? So this is actually not 1, this is going to be 40 in hex. And then we've got so that's actually the last data bit there, and then the 2 stop bits are 1, 1. Okay. Okay, so here's an example question I might ask. If we have 9 data bits, least significant bit first, even parity, 1 stop bit, but we have we don't know what the bit is here. Now, this, by the way, is called an erasure. An erasure is when the receiver knows that there's an error and it knows where the error is. And so with this parity, we can correct an erasure. The problem is if we don't know where the error is, and usually you don't in this case, then all you could do is tell if there's an error. You can't fix the error. In this case, we can fix the error simply because we know which bit is wrong. So if there's even, what did I say there was? Even parity, there should be an even number of 1 bits. However, that's only in the data and the parity sections. So the trick here is that you have to count the 1 bits, but you have to disregard the start and the stop bits, which, well, there's only 1 stop bit, and there's always just 1 start bit, right? So I have to ignore this guy and ignore this guy and count the number of 1 bits in between. So I've got 1, 2, 3, 4, 5, right? So 5 1 bits, which shouldn't be possible in even parity, which means that I know that that missing bit must have been a 1 to give me 6 bits, 6 1 bits, which would be even, right? So that should be a 1, right? So this kind of, yeah. Now, by the way, I didn't reverse the bits because I wasn't trying to actually read what the data was, but the data in this case was 0, 6D for transmit and 0EE for receive. And the parity bit, was 0, but keep in mind, you're not really trying to explicitly look at what the parity bit is. You're just counting the total number of 1 bits, including the parity bit, right, is the goal. So the parity bit was 0. And so did I say what the, no, I guess I didn't give the answer there. But yeah, that missing bit should have been a 1. Okay. Assume a UART channel operates at a baud rate of 9600 bits per second. Oh, by the way, with the Arduino framework, IDE, one of the things I really like about it is you can set the baud rate in your code. And then when you set up your local console, your serial console, you just match that to whatever you told the code said to use, which is nice because normally you don't know, like if you have a new device, right? Like let's say I plug into this scope. I don't know what baud rate the scope uses. So it's trial and error time, which isn't fun. Unless I read the manual, and I never read the manual. The manual would tell you that, but who reads the manual? So I just try every possible baud rate until I get it right. You know when it's right, because if it's not right, you get garbage. Okay, so 9600 BPS, 7 data bits. By the way, what's the unit? Baud rate is BPS. I would say hertz if it were me, but no, BPS. That's a little misleading because the BPS is bits per second, which technically is right. I mean, but you would think that when you say bits per second, I'm like, how many bits of data am I getting through? But that's the bits per second for the data plus all the overhead, right? All the extra stuff. So that's what this question is asking, actually. If there's 9600 bits per second baud rate, 7 data bits, 1 parity bit, 1 stop bit, there's 7 plus 1, 1, and 1, because there's always 1 start bit too, right? So start, stop, parity, that's 3. So that's basically, I just get 70% of whatever the baud rate is in terms of my actual data payload, right? So that would actually be 6,720 bits per second of data throughput versus the baud rate, which is 9600. Now UART, by the way, you don't typically max out the UART channel, usually, because UART is usually used for console. So unless you can type really fast, right, you probably aren't going to max it out very often. I mean, of course, when you're printing logs and stuff, you might, like if you dump a bunch of text or something, maybe, but. Okay, here's another question. What bit is missing? Odd parity, 2 stop bits, 1 start bit. So if it's odd, I've got 1, 2, 3. 3. There's 3 1 bits in there. Remember, I'm not counting the 2 stop bits. So that parity bit must be 0, right? Because 3 is already an odd number. So that should be a 0. Are there any errors in the transaction below? So odd parity, 1 stop bit. Okay, the transmit looks good because there's 1 1 bit, which is odd. The receive side, I've got 1, 2, 3. That's odd. No, I think we're good. I don't think there's any errors in there. Oh, receive. No, I guess I was wrong there. How am I wrong? 1, 2, 3. Oh, 4. Sorry, 1 stop bit, not 2. Sorry, I was thinking 2 stop bits. There's 1 stop bit. And so this one has 1, 2, 3, 4. 4 1 bits. So yeah, the received parity is wrong. So there's an error in there. We don't know which bit is an error. if you're using the Arduino IDE and it detects an error, what does it do? Don't know.
Resend it.
When you're
It resends
when
it?
you're uploading code, I think it just resends it. But
Resend.
when you're using the serial monitor, you just get an error.
Does it print error message or does it give you a
You just
weird
get
character?
You
Like get garbled?
character.
Oh, so it just ignores the errors effectively, right?
Yeah, because
Yeah.
it's just sending text. When you're
Okay.
uploading code, it'll retract.
Yeah. So if you're downloading a program to the chip, it'll retransmit if there's an error. If you're printing stuff on your code, it just lets the error through.
That's all you can do.
Yeah. Okay, so that is UART. All right, so let's see. How much time do I have left here? 1:05, got about 10 minutes. Okay, one last topic before we go. I mentioned SPI has a master-slave, and I only showed you one master, one slave. Is it possible to have more than one slave? You might say, well, why would you want that? Well, I mean, you buy a chip and it's only going to have a limited number of SPI master channels, masters, right? Well, let me clarify that. Chips have hardware. Generally, SPI is designed in hardware, right? And so you'll have a limited number of hardware SPI modules. How many do we have? Do you know, ESP32?
I believe the one we're using has 3, but only 2 of them are useful to us because the third is used by the flash chip.
Okay, so 2. So if we're using SPI peripherals, we're limited to 2, right? Unless we do software-defined SPI, which is kind of a waste of the CPU's time. Or we can use multi-master SPI, which I've never seen a peripheral support this, but I'm told that it exists, right? Never seen it actually done in practice. There's 2 ways to do it. One way to do it, now either way you do it, by the way, requires changes to the hardware. Because one way to do it is to have multiple slave select bits, 1 per slave. That's the easiest way to do it. That way, I just choose one of the slave selects corresponding to what slave, and the other 3 wires, clock, MOSI, and MISO, are just shorted, connected to all 3 slaves, right? The problem with that, though, there is an issue with that. MISO is coming back, which means if I short all these guys MISO to 1 physical wire, then they better have tri-state drivers on here where they can disengage, right? Because otherwise, SPI is, and I'm going to talk more about this when I get to I²C, but SPI uses a push-pull system where the wires are either pulled up to VDD or they're pulled down to ground, right? So if I have one of these slaves pulling up and the other one pulling down, then it's going to result in a short circuit or low impedance path between power and ground, right? Unless there's a third option, which is to tri-state the MISO, right? Which is theoretically possible, but you have to make sure it's doing that, right? You got to make sure that if I use this type of multi-slave select, only the slave that's actually participating is going to engage its MISO line, right? The other option is to use a system that's actually employed by JTAG in reality, is to use a daisy chain. Remember I mentioned that SPI can be thought of as a shift register? You can take that concept forward and you can have the MOSI of the first slave connected directly to the master, but then the MISO coming out of the first slave is connected to the MOSI of the next slave, and the MISO of the next slave connected to the MOSI of that slave, and the MISO of the last slave connected to the MISO of the master. So in other words, MISOs are connected to MOSIs when you go from slave to slave, except when you get back to the master, it's MISO to MISO, right? So what's happening here is that I can get away with 1 slave select, but whenever I do a transaction, it's no longer, no, sorry, I always get the terms screwed up. It's not transaction. Whenever I do an exchange, that's when I do a swap. An exchange would no longer be 8 cycles. An exchange would have to be 24 cycles, right? Because what happens is I'm going to take whatever's in the master and I'm going to first move it through the first slave, then the second slave, and then the third slave, right? So all 4 of these devices will cycle 24 bits through instead of 8 when you have 1, right? So I'll have 24 bits move through the shift register. The problem, though, is that like the first 8 bits are going to cycle through the first slave and then they're going to be gone. So hopefully if this guy needs that first word, he'll have grabbed it, yeah. So it's complicated. Either way, it's complicated. Either you got to worry about tri-state drivers on MISO or you got to worry about these really big exchanges, right? So it's a kind of a pain either way. I've never seen this done. Have you ever seen a multi-master SPI? I've never seen it. I'm told it happens, but never seen it in practice. But this is a nice example though, because there's another protocol called JTAG that works exactly like this. And so if you understand this, you automatically know JTAG, basically. JTAG has one other detail though called test mode select, which I'll talk about. But the actual way that the data is moved through the system. So when you program the FPGAs in 3.13 and 6.11, you were actually doing this. You just didn't know it. Oh, well, that's a good question. So in that case, they're doing UART on top of JTAG. So that's a great point. When I was talking about UART, like when you plug a phone, you plug your iPhone in to write code. There is a console you can print, but yet there's no actual transmit and receive wires. What's happening there is when you plug the iPhone in or an Android phone, you connect to JTAG, and then JTAG is used as the underlying protocol for UART and other stuff like debugging, GDB debugging and programming and all that other stuff, right? Just like with the Arduinos, the UART is actually built on top of USB. It's being conveyed with USB. So what I'm saying is this is kind of a lie in a way, because there's actually no actual UART wire connected between the ESP32 and your console. It's being conveyed over top of USB. And I have no idea how that works. I mean, USB is a packet-based protocol, so presumably you're literally sending packets containing characters that are being conveyed over the serial, right? I think that's how it works. You know, which makes me wonder, why do we care about the speed then? Transmission speed? I don't know. You still have to match the baud rate, but it's actually all a lie because it's virtual. It's over USB. So I don't even know why we're matching the baud rate actually but you still have to match the baud rate. This is assuming that you actually have physical connection. And when we talk to the scopes later in the semester, we do actually have physical transmit and receive wires. But in that case, it's going to be bundled in RS-232. Any questions about that? Okay, so that was multi-master. Okay, so I'll leave it there. So I think what we'll do next class, we'll just work in the lab for a while. And then after the project's due, then I'll get back to lecturing. I'll talk about I²C because the next lab will be I²C on the hardware. We'll be doing I²C on the actual boards. We won't be using software decoding anymore. Okay? Sounds good. Thank you.